after the 30 minutes, the yellow color has disappeared. And it could be because we already used the 0.285, which was closer to 0.3. Now we have our reaction complete. So we have excess of sodium borohydride. We need to remove or destroy the excess of the sodium borohydride by adding this mixture into a 5% hydrochloric acid solution, which we are going to make that. So in the fume hood, in order to make our solution, it's not like very accurate. So this is not like quantitative analysis. We're going to add enough ice to mark of 100 and add some water. Okay, so I added the ice. I add some water to the mark of 100 in the beaker. So I'm using larger size of the beaker. So I have ice water to the mark of 100. Now we measure 5 milliliters of concentrated HCl, and we add the 5 milliliters slowly to the ice water. Now we have prepared our iced HCl solution. It's just 5% solution. We're going to add the mixture, the reaction mixture to the HCl solution. Is going to react, the excess or leftover of sodium borohydride is going to react with the HCl. The hydride ion from the sodium borohydride with the hydrogen ion from the acid, it generates hydrogen gas. So you see that it's bubbling, it's foaming, and it's going to whip the product. And this whipping of product is going to create some trouble for us. Drying and filtration of this product is going to be very challenging, which we have to deal with it. But we need to remove the excess of sodium borohydride first. Add slowly and mix it. See the foam or the hydrogen gas that is generated. Going to whip the product. Transfer the solution, but we want to keep the magnetic bar or stir bar to submit to return to desk, because we don't want to lose that. So it's a whipped product waiting for the HCl, for the ice to dissolve, and also some of this foam kind of settles down before I do the vacuum filtration. Now, for the vacuum filtration, we're going to measure the mass of the watch glass and the filter paper. So we have the mass just in case we are using this as the final. The mass of the watch glass and filter paper for reduction of ketone is 48.392. Our vacuum filtration is already set up. We just add the filter paper, add a few drops of water to the filter paper in order for it to stay still, and it covers all the openings of the filter paper. I'm going to filter this whipped product. It's going to be challenging. Turn on the vacuum because it's foamed or whipped. Okay, after you transfer all the mixture to the Buchner funnel, you can use some additional cold water, as we have a cold water always prepared. For one person, I can prepare just beaker of water. For the class, we place the wash bottle like the DI water in the big ice box to cool it down. So we can continue with the filtration and washing with cold water. I wanted to show you this part. See, the vacuum flask cannot be more than 2/3 full. If this happens, you have to stop the vacuum. Even though we have the trap, but still it's dangerous. We don't want any liquid to go into the vacuum system. You stop the vacuum, you remove the vacuum flask, empty the water, you remove the vacuum flask, empty the water, and take it and set it up again to avoid any water going into trap or into the system. Then you can continue. When you have high volume for the solvent, this happens. It's not often. Then we wash it with about 20 milliliters of cold water 2 times. For washing, we turn off the vacuum. Pour the washing solution over the crystals for it to soak. Then turn on the vacuum. You saw the product, how it was whipped due to the hydrogen gas that was produced in the reaction. So this crystal is kind of unusually thick. And when it's this thick, vacuum is not strong enough. Even this vacuum pump is not strong enough to remove the water completely. So we can press it down with backup clean beaker to help for the water to be removed. And when you do that, want to make sure you don't lose a lot of product here. It does help. We run the vacuum for like 5 minutes to make sure as much water is removed from the crystals. After the 5 minutes, it's been 5 minutes. When it's been 5 minutes, you remove it. You see, you still have like a thick cake. Is whipped, or it was whipped. Now water is trapped between the crystals. Drying the sample with the oven is not very successful because what happens, the surface of the crystals, it gets dry, but inside still is wet. It traps a lot of water. Air drying of the sample is more successful. So what we do, we leave it in the cabinet for the student sample overnight for it to dry. And when it's completely dry, we come back and we measure the mass, we measure the melting point. I also want to explain to you, I said earlier that we might need the mass of the watch glass and the filter paper because I can use this product as the final product now after it's dry, or if there is impurity of the fluoronone left over, I have to do recrystallization. When I do recrystallization, it's going to remove any impurity that is not water soluble, so that would be leftover of the reactant. If the IR shows that there is no impurity of a ketone left over, I don't have to do recrystallization. So I'm going to do a couple of things. I'm going to dry the sample. I'm going to determine or do the IR spectrum of the sample to get the IR spec of the sample, and also measure the melting of the point of the product. If the melting point of the product is close to the literature value, if the IR shows that there is no ketone left over, so it means that the sample is pure. I don't have to do the recrystallization. But if one of those is off, If the sample is dry and still melting point is very low, then I have to do recrystallization to make sure that the sample is pure. So it's going to take a while. So we're going to stop the recording at this point. We come back, we continue when the sample is dry. This sample, it looks dry, and I hope that it is dry, but it's been more than 24 hours left in the sample cabinet. I suggest the students to leave like for a week. And then I also left it in the oven for 15 minutes after that. So we have the mass. This is the mass of the product. I'll take a picture of that. Okay. Again, because the sample was whipped and it could trap some water into this, like inside these pieces. The surface is dry, I can touch and still dry, but it could be some water trapped in there. The mass could be slightly higher. I try to get the sample from the area that is like more powder and smaller particles, to make sure that no water is in, or it's the drier sample basically for the melting point. And let's measure the melting point for these products. Just to make sure that the sample I'm measuring the melting point is completely dry, I put very small sample size basically in a secondary watch glass, and I placed in the oven for additional 5 minutes. The oven was just set at over 100. It's like 102 degrees to evaporate the water. And this sample, that is even more dry than the sample that I measured the mass, because it can get into the capillary tube easily. And we pass it through a glass tube to get the sample down. Okay. The sample is all the way down with no air trap in between, and about 2 to 3 millimeters of the sample we're going to place in the melting apparatus, and setting of the power regulator, because the expected product is going to, the expected melting point for the product is 155 to 157. So around 150, the setting of the power regulator, it should be between 4 and 5, closer to 5. So we will set the power regulator close to 5. Place the sample, turn on the melt temp, and wait for the melting to happen. And as soon as a few crystals of the sample liquefies, and I could see the liquid, a drop of the liquid on the sample, I can record the initial melting. Just be careful not to record the sweating of the capillary, because that would be the water or the liquid that forms on the capillary tube, but on top of the sample, not touching the sample. This liquid is actually should be in the part of the sample, not on top. If you see the sweating on the capillary, that's just terms called sweating of the capillary, and that's not initial melting. Okay, so we are going to wait for this, and since it's taking time, the sample initial melting has started at it's 150. Let me take a picture also here quickly before the temperature goes up. And the final melting at 153 almost. Taking picture. They're not sample, the template. Now, the melting point, it suggests that sample is dry and is expected to be pure because it's close to the literature value. The sample, the mass of the sample was slightly higher than the theoretical value, but that's also understood based on the sample. And these are the points that you need to mention in discussion and also in conclusion based on the percent yield. Since the sample, the IR suggests that there is no ketone left over and is only alcohol, and also the melting point was decent, I'm going to skip the recrystallization. And for students, when you are doing this experiment in class, the professor is going to decide based on your sample if the recrystallization is needed or if you can skip the recrystallization. Normally, if you do the IR before the recrystallization based on the IR spectrum, if there is no ketone, you can skip the recrystallization, which that's what happened here. And if you have to do recrystallization, a recrystallization solvent of 1 to 5.5 water methanol mixture is used for recrystallization. And please, again, check the pre-lab question, pre-lab discussions for this experiment for the theory. And when you're writing a lab report, include the IR values in abstract, in discussion and conclusion, as well as in the data table, along with the melting point and percent recovery of this product. Thank you.